Hello students, welcome back to the session. In today's session, we are going to discuss once again the next topic in the chapter of alternating currents. The topic that we are going to take is combination of the components. Till now what we have discussed is how each component, say R, say L, when alone they are placed with the AC source, how do they behave individually, that we have seen. Now we have to see when the components are placed together in combination, then how do they behave. This is what we have to see. Once again students, out here our aim is to find expression for current. Our aim is to find what is the phase difference between the applied voltage and current, and our aim is to find what will be the power consumption in the given circuit. So these are the three features that we have to extract from the given circuit. So what the circuit diagram looks like? The circuit diagram is something like this. This is R, this is L, and we have connected a AC source. So we have what? AC source, when we say, we know it is E is equal to E naught sine of omega t. This is the source property. Peak value is E naught, frequency is omega, or you can say normal frequency is F. So our aim is to find I. Now since we see that this is a series circuit, L and R, this is series. So what can we say? In series circuit there is a potential drop across R. We can use Ohm's law. There is a potential drop across L, which is said to be induced EMF. So it appears that we can say E is equal to potential drop across resistance. V is equal to V1 plus V2, we say na, plus potential drop across inductor. It appears that we can take this, but please don't commit this mistake. This is wrong. This statement is wrong. You cannot say it is equal. So the question arises, why? Till now you will say we were studying that in series circuit we say V is equal to V1 plus V2 plus V3. Correct. That is very right. But please pay attention on the kind of source which you have placed. Here the source is fluctuating, and there where you have done V is V1 plus V2 plus V3, what is the kind of source there? It's a DC source. So that equation is limited to DC circuits only. That cannot be used universally. Please remember that. This is the concept which has to be understood. Now you will say, why there is a difference? Very right. DC source does not change with time. Frequency is 0. But an AC source fluctuates with time. So what happens? Very right. We have seen in the previous class that in case of R, the phasor diagram, if you see, we have seen that current and potential drop across R, what is the phase difference? 0. Phase difference is 0. Now when it comes to L, if you remember, the phase difference between the current and potential was 90 degree. It was 90 degree out of phase. How can we add now? Can we add these two? It is not possible. How can you add? Then why do we have vector addition? Why do we have Pythagoras theorem and all? When to use that? That is why don't simply substitute some equation that you know and say that this equation is right. No. they all depend upon what are the properties of the circuit. So what we will say, if I try to plot this particular phasors, see, it will look like this. This is current I, so this is ER, this is EL. How will you find resultant of these two? Can we add them? We cannot. That is the reason why in AC this equation does not hold. This equation holds only in DC circuit. So the resultant of this will be somewhere like this. This is the resultant, and this will be the angle at which it will act. So how much will be now? Ez. So therefore what we can say, Ez square is equal to ER square plus EL square. This is how you are supposed to find E, or the net potential difference in an LR circuit. ER is what? We can say I into R whole square. EL is what? EL is I into XL. If you remember, in the last class we had done this. We had seen this in the last class. What did we see? I naught is equal to E naught by R. Also we had seen this is equal to E naught by XL. So using these two, what we can say, E naught across R is nothing but I naught into R. E naught across L will be what? I naught into XL. That is exactly how we can find out the potential drop if we know the reactance. What is XL? XL is the inductive reactance. R is what? Resistance. So what we can say now? We can take I square common. We have R square plus XL square. This is what we have. Now I can write this as I into Z. What is this Z? So we get Z as root of R square plus XL square. What is this Z? Closely observe. This Z is made up of what? It is made up of R. R is what? Resistance. It is made up of XL. And XL is what? XL is also resistance. It is known as inductive reactance. It is the resistance offered by an inductor to an AC. So this equation is the resultant resistance of LR circuit. It is the net resistance of LR circuit. It is known as impedance. If you are aware of the simple meaning of impedance, the simple English word, it is a synonym for resistance. Impedance is a synonym. Now, resistance is a keyword which is reserved for DC circuit. So when you come across the word resistor, resistance, this means it will naturally be a DC circuit. But suppose in the numericals you come across the words reactance, impedance, it implies we are talking of AC circuit. So these are the clues by which you can make your approach to the numerical easier if you know these terms. And if you think that I will remember this equation, I will fit the data, such questions will not be there in any entrance exam. So impedance is given by root of R square plus XL square. This is the net resistance of an LR circuit. Now the question arises, what will be the expression for current? We got Z. See, that is why we wrote E with a subscript Z. This means this is the resultant voltage of LR circuit. Numericals are based on this equation, remember. It will be based on this equation. Now, what is this angle phi? This angle phi is the phase lag between current and applied voltage. See, in case of R only circuit, what is the phase difference? We have seen here. In case of R only circuit, the phase difference between the current and the applied voltage is 0. Come to L only circuit. The phase difference between the current and the applied voltage is 90 degree, where we find that the current lags applied voltage by 90 degree. This we have seen in the previous class. We have done the derivation. Now, if these two are placed together, the phase difference will lie between 0 and 90. The phase difference will lie between 0 and 90. So, this is that angle. So, how much will be that angle? If you see this, this is known as impedance triangle. In the impedance triangle, we can say tan phi is equal to EL by ER. So, tan phi is EL by ER. EL we can substitute from here. We got I into XL and this is I into R. So, tan phi is what? XL by R. See, we got the angle. So, this angle, we know XL. How much is XL? Omega L. So, XL is known to us, R is known to us. We can find this phase angle. Phase angle is known. The next step is whether it is lag or lead. Now, what type of circuit is this? Inductive circuit. Why? Because R and L is there. R will not oppose the current. We have seen that. L will definitely. So, it is a inductive circuit. Remember, this is not a purely inductive circuit. Every word is important. In physics, to solve numericals in the first trial only to get the answer, every word is important. Don't transform the question based on your comfort and based on what you know. So, if it is given inductive circuit means that inductor is in series with other component. If it is given purely inductive circuit means it is L only circuit. So, many things are implied. That depends on our skill to understand the English words in the statements that is forming the question. If we are not able to decipher the words which are there in the question, probably that is our shortcoming, not the question is difficult. Tan phi we got. Next step, our aim is to find the expression for current because E is known to us, na? We need current. So, in an purely inductive circuit, what did we see? What is the expression for current in a purely inductive circuit? Purely inductive, what is the expression for current? I is I naught sine of omega t minus pi by 2. This is what we have seen. In a purely L only circuit, it is this. So, for in LR circuit, that to AC circuit, the expression for current I is I naught sine of omega t minus phi. Omega t. This will not be 90 degree, it will be between. So, the range of phi phase is 0 to pi by 2. The angle will lie between 0 to pi by 2. See, and the equation confirms it. So, lot of numericals will be based on this kind of concepts. This is exactly what we have the expression for current. Now, we have expression for current. We know what is the phase difference. Two things we are knowing. Finally, we have to find out power consumed. So, let us calculate now what will be the power consumed in an LR circuit. So, power consumption. How to find? Same thing, instantaneous power. Small p is what? We know E into I. This is instantaneous power. E is what? E naught sine of omega t. And I is what? I naught sine of omega t minus phi. We had seen this. So, expand it. We can write this way, E naught I naught sine of omega t into sine omega t cos phi, sine A cos B minus sine B cos A. See here, we can write like this. I have expanded. So simplify it. So E naught I naught, if I simplify this, sine omega t sine square omega t cos phi. Here we have a sine phi, and we can write this as sine phi whole divided by 2 and sine of. This is exactly how we can simplify the given expression. This is what we get as instantaneous power. Now our aim is to find average power. So average power is we have to integrate summation p dt over the given time period of one cycle. So limits will be from 0 to t. So please try what you will get in this. So what we get now? In order to do the integration, so what we have? P average is integration of P. So E naught I naught, and this I can take as T. So we get this as E naught I naught by T. Cos phi again can be taken outside, cos phi. So I will put a bracket. Integration of 0 to T sine square omega t dt. This one, then minus, this is sine phi by, this we will call as I1, this we can call as I1, minus E naught I naught by t sine phi by 2 integration of sine of 2 omega t dt from 0 to t. This is second one. Two parts are there, na? Now what we get? E naught I naught by t cos phi. What will be the first integral? We have seen this in effective value of AC when we did the derivation. Integration of sine square omega t from 0 to t over one complete cycle is t by 2. What about this? This will be 0 because it is sine 2 omega t, which is a continuous function which varies from -1 to +1. So the average of such a continuous variation will be 0. So this is what we have as average. So writing it in the proper form, average E naught, see this t cancels out. So we get this as ERMS, E naught by root 2, I naught by root 2 into cos phi. See, this is the average power consumption of an LR circuit. The question is how to verify this equation is correct or not. Because whatever equation you will get, that has to be verified it is correct for the given situation. So how to verify this? See here, let us say we have a purely resistive circuit. Purely resistive circuit means what? R only. What is the phase difference between applied voltage and current in an R only circuit? 0 degrees. Put phi as 0. Cos 0 is 1. So what do we get average power? ERMS, IRMS. We have derived this. In R only circuit, the power consumption is ERMS, IRMS. You take L only circuit. In L only circuit, the phase difference between applied voltage and current was 90 degree. Cos 90 is how much? 0. So average power is 0. Perfect. In L only circuit also we have derived that power consumption is 0. So therefore we can conclude that this equation is perfectly valid. So what is cos phi? What exactly is this? ERMS, IRMS is what? ERMS, IRMS is the power consumed. P average is what? This is the theoretical power. This is actual power. This is called power factor. Cos phi is known as power factor. Now, what is power factor? Cos phi will definitely be less than 1. It will lie between 0 and 1 if I take the magnitude. Correct. This means that the average power consumed is a fraction of this ERMS, IRMS. That is why it is called power factor. Actual power consumption should be how much? ERMS, IRMS. But will that actual power consumption happen? No. Why? Because in an LR circuit, R consumes power, L will not. Which means that the power consumption will lie between 0 and ERMS, IRMS. Exactly that. That is why it is known as power factor. Now, how to find the power factor? We can say cos phi, if you remember the impedance triangle, just have a look on the impedance triangle if you have drawn in your notebook. Cos phi, just verify what it will be. Cos phi will be ER upon EZ. This is what we get as cos phi. Check that in your impedance triangle. ER. So what we get? Cos phi. ER is what? I into R. This is I into Z. So power factor is said to be R by Z. Power factor will be R by Z, and it is verified. It cannot be greater than 1. How can you say that? Because Z is root of R square plus XL square. So the denominator has to be greater than numerator. Therefore, the fraction will be less than 1, and it is established correct. So cos phi is R by Z. This is called power factor. So in the numericals, they will give you the true power consumption is something P, and they'll give you, but when the components are placed in series, it is found that the power consumption is this much. Remember, so you should know how to identify true power and the power consumption. Then only you will be able to make out what will be the value of power factor. Remember, phi is not the power factor. Cos phi is the power factor, not even tan phi. Only cos phi is the power factor. Phi is the phase difference between applied voltage and current in that combination AC circuit. Okay, that is exactly how the AC circuit with LR can be analyzed. Now students, let us take the next combination of components, AC with R and C only. Here we are having a resistor and a capacitor, and the source is AC, not DC. So it is something like this. This is what we have as a series RC circuit. Now again here we cannot write E is equal to ER plus EC. We cannot write. Now I hope you are aware of why we cannot write like this. It is, I hope, clear to you. So what we can say now? EZ will be what? ER square plus EC square. So ER, same thing, I into R. EC, also the same thing. We have seen that XC. In a C only circuit we have seen that. So I am writing the same thing as we did in the previous circuit. No difference. So this gives us I square R square plus XC square. So this is what? I square Z square. So what we get now? Z square is equal to R square plus XC square. This is what we are getting. So we can say Z is root of R square plus XC square. What is XC? XC, that is exactly what is XC. Now Z is what? Z is called impedance. Now what is the difference between impedance and reactance? This is also a part of your board question. Distinguish between impedance and reactance. If you have concentrated, you would have definitely come to know we are writing for this capacitive reactance, inductive reactance. Now this is impedance. See, we didn't write there capacitive impedance, we didn't write inductive impedance. There is a meaning. Why don't we write like that? Impedance is net resistance, net, and net cannot be of a single term. Net will have minimum 2 terms. It can be more than that. Net cannot be for a single term. This means impedance cannot be of one component. Reactance is of one component. That is why inductive reactance, resistance offered by an inductor alone, that is inductive reactance. So reactance is the resistance of a pure component. Impedance is net resistance of 2 or more components. See the difference? That is exactly how we can find out the difference. Eventually you will come to know how to distinguish and all. So we got impedance. Now how will you represent the phasor diagram here? Very important. This is I and this is ER, correct? In this case, this is I, this is EC. If you remember, we had derived in capacitors, current leads applied voltage by 90 degree. That is why observe, in the previous circuit I had drawn EC down. So here we have to show it up. This is what is the representation, because direction makes an important role. How? Lag and lead, how will you distinguish? I will distinguish by the direction. Both will be represented in opposite direction. There is no rule that EC will act in upward direction, nothing like that. You can take this in downward, EL in upward direction. The requirement is the two should be in opposite direction. That is more important. And here what is the phase angle? 90 degree. So if we try to draw this particular feature, then what do we see? This is the direction of current. This is the direction of potential drop across the resistance. This is the direction of EC, we can say. So resultant will be what? Something like this. This is the resultant. This is our, and this is our phase difference. See how we can, how easily we can generate all those things. And because of this reason only, complete the triangle, you see this thing comes, resultant. resultant, right? And what will be tan phi? Tan phi is EC, this is EC by ER. This is tan phi. Tan phi I into XC by I into R. So we get tan phi as XC by R. In the LR circuit it was what? XL by R. Here it is XC by R. So whether it will lag or lead. Now, in a capacitive circuit we have seen that the current leads EMF by 90 degrees. 90 degrees. In a purely capacitive circuit, it leads by 90 degrees. In a capacitive circuit is what? Where the capacitor will be placed in combination with some or the other component. Then the expression for current I will be I naught sine of omega t plus pi by 2. This is what we get. So I is equal to I naught sine of omega t plus pi by 2. This is the expression for current in a RC circuit. This pi by 2 will be phi, because if it is a purely capacitive circuit, we say plus pi by 2. It is a capacitor with a resistance combination, so here it will not be pi by 2. It will lie between 0 and pi by 2. When it lies between 0 and pi by 2, that angle is phi. How will you define phi? Tan phi is given as XC by R. From this equation we will get the value of phi that we will substitute here. That is how we can find out expression for current. Now, power consumption. If we try to calculate the power consumption in this case power consumption, if we try to calculate, power consumption is same as what we saw in the previous circuit, because observe, instantaneous power. What are the steps that we follow for calculating the average power? We calculate instantaneous power, E into I. This we did in the previous case also. How much is E? E is E naught sine of omega t. And what is I? I is I naught sine of omega t plus phi. Correct? So the expression what you will get? You will get same thing, E naught I naught. In the bracket you will get sine square omega t cos phi. Instead of minus you will get plus. You will get sine phi by 2 sine of 2 omega t. See, what is the difference? There is no difference except this plus was minus in the previous derivation. So instantaneous power is same. So this means average power, I will leave it as an exercise to you to find integration and all those things. Integration of p dt by dt from 0 to t. This is also from 0 to t. Please follow the integration that we have done in the previous derivation. You will get this as E naught I naught or ERMS IRMS cos phi. Same expression you will get. So average power is ERMS IRMS and cos phi. This is what you must get. Again, what is cos phi? Cos phi is the power factor. So power factor, how will you find? From this impedance triangle, we can say cos phi base upon hypotenuse. So you get this as ER by EZ. So ER. So we can say cos phi is, again we get the same expression. The value of Z will depend upon what is the type of the circuit, meaning what are the components placed in the circuit. That is exactly how we can define cos phi, which is a power factor. It will lie between 0 and 1. That is how we can analyze AC with R and C components.